Alrighty. So let's get to the end of chapter 7 here. We're going to start by looking at collisions in one dimension. So we can use conservation of momentum to examine collisions. That means that our external forces to the system are going to essentially be zero. Even if they're not zero, when you have two large objects colliding, any external forces are going to be very, very tiny compared to the internal forces of the system. Okay, so let's look at what we mean by this. So let's say we have mass 1, and mass 2. And they are moving towards each other. And then they're going to collide. Now, when they collide, for the amount of time that they're in contact, the amount of time delta t that they're in contact, they're going to be exerting forces on each other and using Newton's third law. So the force of mass 2 exerted on mass 1, and then the force of mass 1 exerted on mass 2. And so with Newton's third law, we remember that force 1, 2 is going to equal negative force 2, 1. So they're equal and opposite. Then after they collide, this time the change in momentum is represented as a change in direction. And so now they're moving away from each other. So this is the idea of what we're looking at. So let's say we have a 5-kilogram ball that starts at rest and is struck head on by a 2-kilogram ball moving along a track at 10 meters per second. If the 2-kilogram ball is at rest after the collision, what is the speed of the 5-kilogram ball? Okay, so we're going to say we have mass 1, we have mass 2, okay. Okay, so mass 2 is the 5-kilogram ball, so it's not moving to start with. Mass 1, however, is moving. They're going to hit each other. At which time mass 1 won't be moving. Now let's represent it this way. And mass 2 will now be moving. Okay, so we said we can analyze this with conservation of momentum. And so what we're going to have is the momentum of mass 1 initial plus the initial momentum of mass 2. And that's going to equal the final momentum of mass 1 plus the final momentum of mass 2. Okay, so this is going to give M1 V1 initial plus M2 V2 initial, M1 V1 final, oops, M2 V2 final. And then some of these are going to be 0 because initially mass 2 is not moving. And after the collision, mass 1 is not moving. So we're going to have mass 1 V1 initial equals mass 2 V2 final. And so we solve for the final velocity of mass 2. And now we can plug in numbers. Okay, and so your V2 final, that's going to be 4 meters per second. Okay, now we're going to start looking at the concept of elastic versus inelastic collisions. Elastic collisions, total kinetic energy of the system is the same before and after the collision. So this can be, conservation of momentum and K initial equals K final. Okay, inelastic collisions, that's where we're going to have initial momentum equals final momentum, but K initial does not equal K final. Your perfectly inelastic collision, what this is talking about, so let's say we have two masses. One of them is moving, the other one's sitting still. Let's see. After the collision, after the collision, they stick together and now they're moving as a single unit. So that's what we mean by a perfectly inelastic collision. Super inelastic collisions, not really something we're going to calculate, but it can still happen. Your momentum is conserved. However, in this case, your K final is greater than your K initial. Okay, so this is what we mean with elastic versus inelastic collisions. Okay, so let's say out on the road somewhere we have a car that's essentially 150 kilograms stopped at a stop sign. A truck that is 200 kilograms comes up behind and hits the car. The two vehicles stick together and they slide into the intersection. See, initially the truck is moving at 17.5 meters per second. What is the speed at which the car would be pushed into the intersection? So this is a question that's demonstrating a perfectly inelastic collision. So let's kind of look at this. So let's say we have the truck, call it mass 1. And the car is going to be mass 2. We know that initially We know that the truck is moving, the car is sitting still. They hit each other. And so now we have a system where the car and the truck are stuck together as a single unit. And they share a final velocity. So whatever that final velocity is the velocity the car is being shoved into the intersection. Okay, so let's start with conservation of momentum. So we're just going to start here. But we know that since mass 1 and 2 are stuck together, the final velocity of mass 1 equals the final velocity of mass 2, just equals final velocity. Okay, so we also know that in the beginning, mass 2, the car is not moving. So now we can say that we have mass 1, V1 initial equals mass 1 V final plus mass 2 V final, which is going to equal mass 1 plus mass 2 V final, and I factor out the velocity. And so then our final velocity is going to be M1 V1 initial over M1 plus M2. Okay, so let's plug some numbers in there. Oh, let's see. Okay, so mass 1 is your truck. And its initial velocity is 17.5 meters per second. And then in the denominator, we have mass 1 and mass 2. And so when we calculate this, our final velocity of the entire system and the car is going to be 10 meters per second. Okay, so that takes care of one dimension. Let's look at collisions in two dimensions. This is going to take into account that our velocity vectors and thusly our momentum vectors are going to have components. So let's look at a before and after situation. Okay, so let's say that before our collision, we're going to have mass 1, and it's moving with a velocity, some velocity. And we have mass 2 just sitting still. Then they hit each other. Okay, now, this time mass 1 is going off in some direction. And mass 2 is also going off in some direction. The way we can start to look at this by saying, well, let's put mass 1 and 2 So let's see, mass 1 going to have a final velocity vector. At some angle theta, that would be a first quadrant vector. Yep. And then mass 2, I'm going to draw my x-axis up here. Because this vector, this velocity vector, is going to go down and off into the fourth quadrant somewhere. And so you say, well, what is the final momentum of a system like this? Well, it's going to be a total momentum of m1, v1 final. Okay, and then we have to take account of the fact that, so for your v1, it's going to have components. So it's going to have v1 final x is going to be v1 final cosine of theta 1, then the y component, and then also our v2 is going to have its components. Not one. Okay. What this means is that when we analyze our systems, we can actually analyze the x and y directions independently. So for this system, we would do conservation of momentum. So there we have the conservation of momentum in the x direction, and similarly, our conservation momentum in y. So we can split these two directions apart. So this problem is going to be pretty much a logic problem. Can you derive an equation? So you have a ball of mass m1. It moves at a speed, initial velocity, along the positive x-axis towards a second ball, mass m2, which is 5 times the mass of mass 1. The second ball is initially at rest. After they collide, ball 1 moves along the positive y-axis with a speed v1, and ball 2 moves with speed v2 at an angle 37 degrees below the positive x-axis. Find v1 in terms of initial velocity. Okay, so let's look at what happens after they collide. After they collide, I'm going to have mass 1. It's going to be moving off in the y direction at v1. Mass 2 is going to be moving off in this direction. Where theta is a negative 37 degrees. Again, so we're now back to the point where, okay, so we've moved clockwise from the positive x-axis. So that's going to draw out a negative angle. Again, when looking at these velocities, so this is, so when looking at these vectors, again, you can go ahead and plug in the negative 37 and you'll get the correct signs. Also, you could just take into account that theta is a magnitude of 37 degrees, and then you realize that your x component has to be positive and your y component has to be negative for v2, because this velocity vector is in the fourth quadrant. Okay, so how do we start analyzing this? Well, we're going to break it into individual parts. So let's just start with the x direction. Alrighty, so first off, we notice that your V1 initial x is just VI. We can also take account of the fact that initially mass 2 is moving, and after the collision, mass 1 is only moving in the y direction, so there is no x velocity. So we say that we have m1 vi into v2 final x. So this is going to be m2 v2 cosine of negative 37 degrees. And so now we're using a trigonometric identity that the cosine of a negative angle is just the cosine of the angle. Okay, so you can look this up in tables of trigonometric identities, but we're going to make use of that. And now we also make use of the fact that m2 is 5 times mass 1. 37 degrees. Now take the cosine of 37, multiply it by 5. And this is going to give me, so m1v initial, it's going to be 3.99 m1v2, divide through by m1. Okay, so we can start working with this. We don't know what v2 is, but let's now work in the y direction. All right, so let's do our conservation of momentum in y. Okay, so m1. Let's see. Yep. Initial velocity in y. M2. Initial velocity in y. Initial velocity in y. We're going to have m1 v1 final in the y direction plus m2 v2 final in the y direction. Now, of course, initially, mass 2 is not moving. Also, initially, mass 1 is only moving in the x direction. And so now let's work with this. So we know that V1 final is just V1. And then our V2 final in the Y direction, it's going to be mass 2 V2 sine of negative 37. Again, same trig identities. So sine of a negative angle is the negative sine. Okay. And now we're going to plug in 5.0 times mass 1 for mass 2. All right, and then multiply 5 by the sine of 37. All righty. Now I can take the 3.01 across. And so then V2, because I need to substitute in V2, so I need to find what it equals. Okay, so I see that the M1s are going to cancel out, and my V2 becomes V1 over 3.01. Now, I'm going to take that and plug it back in to here. So now, my V initial this is now going to become 3.99. V1 over 3.01. The initial, so I'm going to divide 3.99 by 3.01. It's going to give me 1.33 V1. However, the problem told us to find V1 in terms of VI. So that means I'm going to divide through by the 1.33. I'm going to get V1. The initial. And so finally, V1 is going to equal 3/4 of V initial. And that's the final velocity of mass 1. Okay, so that finishes up this chapter. So I'm going to have to do another re-recording to start the chapter on torque. And so we will continue there in a little bit. All right, thank you.